In this video, we are going to talk about properties of liquids. The first property that we're going to talk about is viscosity. What is viscosity? Viscosity is a measure of how easily the liquid flows. So does it have a high resistance to flow or low resistance? The higher the resistance to flow, the higher the viscosity is, the more viscous the liquid is. We are all familiar with viscosity because we have, all of us, seen how difficult it is for honey to flow in January, for example. Or you might have heard the saying, the expression, slower than molasses in January. Well, what does that mean? That is the resistance to flow of that particular liquid. And honey, especially, and we'll see in class as well, we'll see that viscosity depends on temperature, but the lower the temperature, the higher the viscosity is going to be. And some liquids pour out, so basically they don't resist the flow. They pour out very easily, as other liquids that don't. When we pour out honey, for example, versus water, well, honey is a lot more viscous. And if we look to what is the key to how a liquid flows, it's going to be, you guessed it, the intermolecular forces. Those are very important in the physical properties of liquids and solids. How do intermolecular forces affect viscosity? The higher the intermolecular forces are going to be, the higher the viscosity. Think of it as kind of a Velcro, right? If those molecules are really attracted to each other, the intermolecular forces are very large. It's going to be like Velcro. They're going to stick to each other. They're not going to want to flow past each other. So if we were to look at water versus honey, well, we know that water flows relatively easy, so it must not be very viscous. Well, what is then the key to honey being very resistant to flow? That tells us that its intermolecular forces have got to be a lot stronger than just water. If you look at how honey is made, what makes up honey, it's made up of a lot of glucose molecules, a lot of sugar molecules, and they have a lot of OH groups, just like this. And it tells us that it can hydrogen bond a lot more than water does. And that is why its intermolecular forces are very large, and that is why honey is more viscous than water. So the stronger the intermolecular forces, the more viscous a liquid is. So here's two different compounds that are being poured out here, and one of them is more viscous than another. It's kind of hard to judge from this picture, but this is the molecule to the left and this is the molecule to the right. Well, I can see they're very similar to each other, and they have similar molar masses, right? They're not that different. But what I do see is that these molecules are polar because they have these OH groups. And not only that, but they can hydrogen bond because they have an oxygen that's directly bonded to a hydrogen. The difference, though, is that this molecule can hydrogen bond in two places, so can double hydrogen bond, if you will, whereas this molecule has three OH groups, which means they can hydrogen bond in three places. Therefore, its intermolecular forces are stronger than this molecule, and because they're stronger, this molecule here is going to be more viscous. Let's talk about another property of liquids, and it's called surface tension. Maybe you have seen this, maybe you haven't, but if you haven't, just go on YouTube. I'm sure there's somebody that has done this, but you sometimes can actually put a pin right on the surface of the water, not by its head, but the long way, and it will lay on the surface of the water. Even though it is actually denser than water and it should fall, it still stays on the surface. Or there are bugs that actually walk on water. They look like that. Why is that? Well, those are examples of what is called surface tension. And I just mentioned water, but any liquid really has a surface tension. Now, once again, this is going to depend on intermolecular forces. If I have a liquid right here, and these are the particles that make up the liquid. If I have this particle right in the middle here, well, this particle is being pulled on all directions by these molecules around it. If you can think of it three-dimensionally. It's surrounded by other molecules or particles three-dimensionally, and they're all pulling at it. So the net pull is really zero. It's not moving up or down or to the left or to the right because they're all pulling the same, but in different directions. So that's the bulk inside. Now, what happens to the molecules or particles that are really at the very top? They're on the surface of a liquid. Well, these molecules don't have other particles up on top above them. They're it. And so they experience a net pull downward, right? Because there's nothing to balance it on the above them, on the top. This inward pull of the surface molecules, this net pull downward, is known as surface tension. Now, the stronger, obviously the stronger the pull that is going to be experienced by these surface molecules, thus the higher the intermolecular forces, the higher the surface tension is going to be. Let's talk about vapor pressure in liquids. It's very similar to the solids, but we're now talking about liquid vapor pressure. We have substances that can have very high vapor pressures or very low vapor pressures at room temperature. Those that have very high vapor pressures are called volatile. Those that have low vapor pressures are called non-volatile. We can actually smell the volatile substances very easily in the air because they have high vapor pressures. They evaporate very easily into the gaseous phase, and we can then smell them very easily. A lot of gasoline or hydrocarbons are volatile because they have very high vapor pressures at room temperature. To be able to escape from the liquid or the solid, but since we're focusing on the liquid phase here, from the liquid into the gaseous phase, the molecule or the particle has to have what we call kinetic energy, a minimum kinetic energy, right? It has to have some energy to overcome that attraction from other molecules in the liquid phase and be able to escape and go into the gaseous phase. That minimum kinetic energy, it's required by all these molecules to be able to overcome those intermolecular forces. Now, if I look at, obviously the fraction of the molecules that have at least the minimum kinetic energy is going to depend on temperature. Temperature is kind of a measure of the amount of kinetic energy that a molecule contains. And so if I'm looking at one temperature over here, the lower temperature, if you will. I have measured here, I have marked the minimum kinetic energy that is required versus the number of molecules here, right? So if all of these are fractions of my molecules, this inside this curve is all of the number of molecules that I have in the liquid. If right here is the minimum kinetic energy that is required to escape from the liquid phase, only what appears in kind of an orangey color, only those molecules are going to be able to escape into the liquid phase because they have more than the minimum kinetic energy that is required. The rest of these particles that are contained in this white area over here don't have enough energy, so they're still in the liquid phase. Only this part of those molecules are going to escape. What happens if I raise the temperature? Well, what we notice is that these curves change and they start to slide to the right. Note that I didn't change the minimum kinetic energy that is required. That is still the same, even at higher temperature. But what is changing is the number of particles that have enough energy now to enter into the gaseous phase. The shape of this curve is changing. And so now I have, right, look at the red curve here. I have all of these that are found, so all of these particles that are found here from the red curve and on, right, these now have more kinetic energy than the minimum that is required. And so we increase the number of particles that have enough kinetic energy to overcome those intermolecular forces that keep those particles in the liquid phase. At the lower temperature, it's from the blue, right, from the blue curve and downward, this fraction. But at higher temperature, it's going to be from the red curve and downwards. And you can see how if I increase the temperature even more, it's going to shift further and further. So it's going to increase the number of particles that have enough kinetic energy to overcome the liquid phase. So temperature is important for vapor pressure. The higher the temperature, the higher the vapor pressure. And this is true for volatile and non-volatile substances. Temperature always increases the vapor pressure because it gives those that kinetic energy that is required for the molecules to overcome the liquid phase. Now, what is happening molecularly as I put, let's say I put a liquid without any gas, I put a liquid in a flask and then I observe what happens over time with that particular liquid. Well, at first, I don't have any gaseous particles in that container because I just put the liquid in there. What's going to happen is that some of those molecules are going to have enough kinetic energy to overcome the attractions from other particles in the liquid, and they're going to escape into the gaseous phase. So I start to get a little buildup of gas molecules above that liquid. So I get an increase of vapor pressure slowly. Now, what is also happening is that the more molecules that escape in the into the gaseous phase is going to increase the number of the molecules that are now in the gaseous phase. So you can imagine then, as I'm increasing this number here, well, one of them might get close enough to these liquid molecules to lose that energy as it's moving. It loses it or it collides with the liquid the particles in the liquid and gets sucked back in to the liquid phase, right? So as I am moving here in time, you can see that eventually what happens is I am moving molecules into the gaseous phase, but I'm also bringing down some of those molecules back into the liquid phase. And we reach what is called a dynamic equilibrium because the rate of condensation, so the rate of, so basically a rate is how fast. So how fast molecules are condensing, coming back into the liquid phase, ends up to be the same, becomes equal to the rate at which some molecules are evaporating, going into the gaseous phase. So some are escaping, but others are coming back into the liquid. And eventually it gets to be the same number. So the same number of molecules that evaporates goes into the gaseous phase. It basically that's the same as the number of molecules that are now going back into the liquid that are condensing. Even though these processes continue at the same rate, the number of molecules in the vapor phase is not changing. This is for a given temperature. If I increase the temperature, we're going to increase the vapor pressure, which means we're going to increase the number of molecules in the gaseous phase. However, for a certain given temperature, there comes a time when we reach this dynamic equilibrium, which tells me that the number of molecules that escape the liquid and go into the gaseous phase is the same as the number of molecules that go from the gaseous phase back into the liquid phase. So there is no net change. We call it net change, overall change, but the molecules are not the same, right? We have a change in molecules, but overall, the number of the molecules stays the same, but they're not the same molecules, right? It's similar to being at a fair, for example, since it's the month of fairs. If we have, at first we would have a huge rush of people, right? When the doors open, a huge rush of people comes in. But then there comes a time that there are people coming in and people coming out because they're leaving. If the number of people coming in equals the number of people that leave the fair, the number of people inside the fairgrounds doesn't change because I'm adding and subtracting the same number, right? But the people themselves are different because I'm getting different people that come in and different people that go out. Similar idea here. There comes a point in time where the number of particles in the gaseous phase doesn't change anymore, the number, but those particles are not the same as what I started up here because I'm constantly recycling them, if you will. Here's a graphic description of what we're looking at here, right? At first we get we get an increase, but then there comes a time where there's no more increase. We get this flat line that tells us there is no net change in the gaseous phase, in those particles. The next physical property, if you will, that we're going to talk about for liquids is boiling point. The boiling point is the temperature at which the vapor pressure of that liquid is equal to atmospheric pressure. So if I have atmospheric pressure right here, here's three different molecules. I have diethyl ether, I have water, and I have mercury. If I have atmospheric pressure here, for us, it's 1 atmosphere. That is normal, ordinary atmospheric pressure. It might change slightly, but it's about 1 atmosphere. If I start to increase the temperature for diethyl ether, for example, if I start from minus 80-ish, and I start to increase the temperature, I'm going to increase its vapor pressure, because remember we talked about how vapor pressure is dependent on temperature. The higher the temperature, the higher vapor pressure becomes. Well, the vapor pressure is going to increase. When the vapor pressure becomes equal to the atmospheric pressure, so outside we have pressure from the air around us. That's what atmospheric pressure is. When the vapor pressure of diethyl ether becomes equal to the atmospheric pressure, right at this point here, well, if I draw a line to figure out what the temperature is, that is 34.6 for diethyl ether. Well, at 34.6 degrees Celsius, we say diethyl ether boils, because that is the temperature at which the vapor pressure of diethyl ether is equal to the atmospheric pressure. For water, we know that water boils at 100 degrees. Why is that? Because that's when the vapor pressure of water becomes equal to the atmospheric pressure. And we can argue the same thing about mercury, except mercury is at 357. Now, once again, we can determine the type of intermolecular forces that exist in diethyl ether, water, or mercury, and that will also tell us why diethyl ether has the lowest boiling point versus water versus mercury. Well, it has the lowest boiling point because this molecule really is nonpolar. That means it only has pretty much dispersion forces. Water, on the other hand, is a polar molecule that can hydrogen bond, so it's got a higher, much higher boiling point. Mercury is a metallic bonding. So there's metallic bonding in mercury, and therefore it is much higher than even water because the intermolecular forces are higher. The relationship between boiling point and intermolecular forces is that the higher the intermolecular force, the higher the boiling point. Note that it is the opposite of vapor pressure. The higher the intermolecular force, the lower the vapor pressure, the higher the boiling point. Which makes sense, because if my vapor pressure, which is the pressure of the gaseous molecules above the liquid, if those molecules are held together by high intermolecular forces, fewer of them are going to escape in the gaseous phase. So the vapor pressure is going to be low, and it's going to take a higher and higher temperature for them to escape, for enough of them to escape the vapor pressure or into the gaseous phase to increase the vapor pressure to what atmospheric pressure is, and that's why the boiling point is higher. Make sure that you keep this clear in your head. I cannot tell you how many students get these confused. I always suggest to my students to go back and think of intermolecular forces. In terms of intermolecular forces, what is the relationship between that and vapor pressure or boiling point? The higher the intermolecular forces, the lower the vapor pressure, the higher the boiling point. The weaker the intermolecular forces, the higher the vapor pressure, the lower the boiling point. Here is a sample problem for you to try. Select a compound with the higher surface tension, CH3OH or CH2OH, CH2OH. When you draw the Lewis structure of this molecule, the carbons are bonded together, and they have each carbon is bonded to one of the oxygens, and then two hydrogens as well. I will give you some time to try this problem.